Good morning, everyone. Today we are going to study buoyant force and buoyancy principle. So basically, buoyant force is an upthrust which acts on a body which is partially or completely inside liquid. So let's say a body is completely inside liquid, right? Let's say this body of mass m is immersed in a liquid completely. So this body will experience a net upward force, which is known as the buoyant force, which we are calling as buoyant force, right? So this body of mass m, when it is partially inside liquid or completely inside liquid, okay, as of now it is completely inside. We can take the case also when it is partially inside also on the surface. So this body is floating on the surface with this much part immersed. Again, it will experience some net upward force, net upthrust. So buoyant force we can define as it is the net upthrust which acts on a body which is completely or partially inside liquid, immersed in a liquid. This buoyant force acts on the center of mass of the body, which the portion of the body which is immersed, which is inside, right? For example, in this case, only this much of portion is inside liquid. Only this much of portion is inside liquid. So buoyant force will act at this point, center of this immersed portion, which is inside liquid, right? This buoyant force will be acting here. Okay, and in this case, as complete body is inside, so buoyant force will act here, right? So at the center of immersed portion. Now, this buoyant force will be always vertically upwards. Now let's see why this buoyant force and what will be its value. So why it is acting, first of all. So considering this case only, let's say this height is h1 and this height is h2, right? As we know, pressure of liquid is rho gh, right? It increases with depth basically. Pressure is proportional to the depth. So it increases with depth. More the depth, more will be the pressure. So clearly this pressure at this point, we will call it P2, will be more than pressure at this point, P1. So the force applied by pressure at this point will be F2 and force applied by pressure at this point will be F1, right? We know in a stationary liquid, the pressure is same at a horizontal level. At a given depth, pressure is same. So F2 and F1 are two forces acting on this, right? These horizontal forces, they will be equal, so they will cancel out, right? So net force will be in upward direction only, right? And clearly this S2 is more than H1, so this F2 will be more than this F1. So net force on this body, which we are saying as buoyant force, will be F2, which is bigger, minus F1, right? F2 minus F1. This is the net force and this is your buoyant force only, right? We can quickly write its value also. Let's say area of this base is A, right? And pressure here is P2. Area of this also is A and pressure is P1. So force will be P1 into A and force F2 will be P2 into A. So we can write F2 as P2 into A minus P1 into A, right? Now we can quickly, P2 we can write as rho g H2 and this will come out to be rho g H1 into A, okay? Solving it, we will get rho g H2 minus H1 into A. Now you see H2 minus H1 is this distance, this H of this body, right? And A is the area of this base. Let me redraw this object. So this object looks like this. This is from the top, this is H1 and this is H2, right? So H2 minus H1 will be this depth, this length, the height of your box, and A is the area of this base. This area is A. So A into H becomes its volume, right? We can write H2 minus H1 as H only. So rho g H into area, and this becomes the volume. H into area becomes the volume. So basically, Buoyant force finally comes out to be density of liquid. H into area is the volume of body which is immersed in the liquid, which is inside the liquid. So we will call it V inside and multiply by G. This is the value of Buoyant force, right? So here we get to know, if we have to write the Buoyant force, we certainly don't require to write F2 and F1. We can directly write the density of liquid, volume which is inside, volume which is immersed, the volume of object which is immersed, and gravity. This will give our answer, right, of Buoyant force. This will give the value of Buoyant force, and we know it is vertically upwards, and it acts on the center of gravity of displaced liquid, or rather the center of gravity of immersed portion, right? So this is the value. This is valid for all the cases. Either the body is partially immersed or completely immersed, the Buoyant force will be this much only, right? Now let's come to Archimedes principle, right? What he says, and it further makes it conceptually correct. Further make this equation conceptually correct. So buoyancy principle, or the Archimedes principle, so Archimedes principle basically says, let's say this is the initial depth of liquid, initial height of liquid, right? And we have a mass m which we are going to sink in that liquid. So the mass m is completely immersed in this liquid, right? So now this was the initial depth, right? This was the initial height, and when we put this mass inside the liquid, the level of liquid will rise. Some liquid will be displaced, right? When we put a denser body inside a liquid, the level of liquid will rise, right? Remember Thirsty Crow? Thirsty Crow put some stones in the pot, and the level of water has risen. So this level will definitely rise, right? We will call this liquid, this portion which has risen, this much of liquid, as displaced liquid. Right? We can call this as displaced liquid. So Archimedes principle basically says the buoyant force acting on this body, net upthrust acting on this body, right? So Archimedes principle basically says buoyant force acting on this body will be equal to the weight of this displaced liquid. Right? Whatever is the weight of this liquid, we can calculate the weight, right? As we know, the density of liquid the volume how much has been displaced. So we can write the weight by any means. If we can write the weight, we can directly calculate the Buoyant force. Now, sir, how to write the weight? So basically, you see, this was the initial volume of liquid, and this much volume, this was the initial volume of liquid, and this much volume is occupied by your object, right? So if this was the initial volume, let's say it's a complete gas or a complete liquid, right? And out of the total volume, this much is occupied by your object of mass m. So only this much volume will be displaced. This much volume will be displaced. So this volume will be equal to this volume. Okay. So the body which is inside the liquid, this body, the volume of this body, we will call it volume inside. Okay. It might be completely immersed or partially immersed. So volume inside will be only the displaced volume, right? Or we can say only this much volume will be displaced, right? So now we can write weight as the density of liquid is rho L, volume displaced is volume inside immersed, and G. This will be the Buoyant force, right? We can say this directly, that this will be the Buoyant force as we have calculated in the previous slide, right? Now let's do some numerical on this. So the first question will be basic example. If this is a container having two immiscible liquids of density ρ1 and ρ2, there is a container and two immiscible which do not mix, these liquid of density ρ1 and ρ2 are placed in it, and there is a solid sphere of density ρ, which is half in this liquid, upper liquid, and half in lower liquid. So half of the volume, you see, half of the volume is in upper liquid and half of the volume is in lower liquid, right? So we have to find the density of this solid ball. Find the density of solid ball, right? So this solid ball is, the question is, the solid ball is half in upper liquid and half in lower liquid, is at rest in this position, is immersed in this position, and now we have to find the density of this ball, right? So what we can do is, using this Archimedes principle, we know that since the body is at rest, first of all, since the body is at rest, so upward force, that is Buoyant force, net upward force, must be balancing mg, right? There are only two forces on this body, Buoyant force and mg. They must be balancing each other. Now we can write this Buoyant force due to two liquids. There are two liquids of density ρ1 and ρ2, So we can write this Buoyant force due to both the liquids and equate it to the weight of the body, right? So our equation will be Buoyant force due to liquid 1 plus Buoyant force due to liquid 2 is going to be equal to mg, the weight of your solid ball, right? Mg we can write as density of your solid ball, which we have to find its total volume into G, right? So now let's write the Buoyant force due to liquid 1. In liquid 1, we know Buoyant force is density of liquid, volume inside liquid 1. So volume is, half of the volume is inside liquid 1, right? So it will be half of the volume into G. This will be the Buoyant force due to 1. Similarly, due to liquid 2, Buoyant force will be ρ2, volume inside, into G. And this will be equal to density of your object into volume into G, right? So from this, we can write the density, we get the density of this solid ball as, solving this equation, we will get directly rho 1 plus rho 2 by 2, right? This we can write directly, है ना? Using the buoyancy principle, Archimedes principle, right? If we have in this question, if we have tried to write F1, F2, right, downward force, upward force, right, pressure at different heights, then it will be little lengthy. The problem, the solution would be very lengthy, but we can do it very in a very subtle way using Archimedes principle directly, right? Let's look at one more problem. So let's say this is a boat which is floating at the surface of water, right? There is a person in this boat and there are some stones. Okay. Now, this person throw the stones into water, right? So in the second scenario, this person throws all the stones into water, right? And the boat is now empty. The weight of the this boat has been reduced. The mass of the boat has been reduced, right? So stones are thrown into water. Basically, we have to find what will happen to the level of liquid, right? This was the initial level. I will call it, let's say, capital H, and this was the immersed portion initially, let's say small h. So the first question is, in this case, in this question there are two parts. Capital H will increase or decrease or remain same. What will happen to capital H? Okay. Second question is small h, same question. It will increase or decrease or will remain same. Right. So this is what we have to find, right? What will happen to both the heights, right? So again, we have to apply Archimedes principle. We will try to find this using, it's a conceptual question. So we'll apply the concept of Archimedes principle or buoyancy principle, right? So let's look at capital H first of all. Let's look at only capital H. Right, this was the initial height, capital H, and initial height is capital H. Now let's say in the first case, buoyant force acting on this combined system of boat and stones is FB1, and in the second case, buoyant force on this combined system of boat plus this stone is FB2, right? The total buoyant force that is acting, our system is this boat plus the stones, right? So let's say in the first case buoyant force is Fb1, in the second case combined buoyant force here plus here, this combined buoyant force is Fb2. Okay. Now we know buoyant force is proportional to the volume immersed, right? The volume of liquid immersed, or we can say more the buoyant force, more will be the volume displaced, right? You know, it is buoyant force is equal to, conceptually buoyant force is equal to weight of displaced liquid. So this is volume of displaced liquid. Right, buoyant force on a is proportional to the volume of how much liquid is displaced, right? So we have to just check in which case the volume displaced is more, right? More the volume displaced, more will be the height of liquid, right? So we just have to check the which buoyant force is more, FB1 or FB2, right? So clearly in this case the buoyant force is holding the weight of stones plus boat plus men, and in this case the weight of this the boat has decreased, right? So in this case, since the stones are thrown in the water, right, inside the water, so the buoyant force on them will be decreased, right? Buoyant force acting on them will be less than weight of these stones, right? If we have to write mathematically, buoyant force in first case will be, let's say m is the mass of this men and small m is the mass of these stones. So we can write capital Mg plus small mg. In first case, mass of men plus stones. Men and boat, right? Plus stones. Right? In the second case, since the stones are thrown downwards, right, the buoyant force on these stones will be less than their weight. Okay? So in the second case, this will be less than, in the second case, buoyant force will be less than mg plus small mg. Right? So clearly we can say buoyant force in second case will be less than buoyant force in first case. Or we can say volume displaced in second case will be less than volume displaced in first case. Or we can say, since volume is less, so we can say height in second case will be less than height in first case. Right? Since buoyant force in second case is less, so volume displaced will be less in the second case and height in the second case will be less. Right? So we can say height will decrease. It will become less than the original height. Right? So the final answer will be capital H will decrease. Right? Second question, if we see, in the second question, we are talking about this small h. Let's redraw the diagram, or we can use this diagram only. So this is small h. We are talking about this small h. This will increase or decrease, right? So logically we can say this, ki because the weight of boat has decreased, the mass of the boat has decreased, right? And some part of the boat, some stones are thrown inside the water, right? So it will become light. The boat will become light, and lighter things race because there is upward upthrust, buoyant force, right? So basically this boat will rise and this h will also decrease, right? So h, we can write directly, since the boat becomes lighter, therefore capital H will decrease, right? So both the heights will decrease basically. Okay.